Welcome to note set number 16. So in the last note set we talked about bandpass signals. Now we're going to talk about bandpass sampling. When we talked about bandpass signals, we talked about how we really want to end up with the equivalent low-pass signal. And the classical way of getting that, we talked about using the analog method, and we saw that we needed an oscillator, 90-degree phase shifter, two mixers, two low-pass filters, and so those oscillators needed to be at the center frequency of the signal, and the mixers needed to operate at those high frequencies as well. Now there are methods where you first do an initial down shifting with just a single mixer and oscillator and bandpass filter, and then do the structure that we looked at, but applied at a lower center frequency. So that is possible, but the trend is to try to go move the sampling as close to directly at the antenna as possible. Now, obviously, that's the trend, and there are some physical limitations, from the electronics point of view, speed and quality of the electronics. So we're not going to address that aspect. We're going to look at it from a theoretical point of view. And as a DSP theory guy, my viewpoint is always, that the theory drives what we need the hardware to do, not vice versa. But there is some back and forth on this. But really, it's the theory that tells us that if we do this, it's something that we can use, and then the physics of it, building the actual integrated circuits and so forth, shows whether we can actually achieve our goals. So this is in section 6.4.1 of Proachus and Monolachus, and I want to start off with just a simple illustration here of the basic idea. So suppose we have a signal here that has a bandwidth B, so we're looking at FH and FL here, and the difference between them is B, and we're also looking at a particular case where FH is strictly equal to 3B. Now, if we look at the classical sampling theorem that tells us we must sample at least twice the highest frequency, we would be looking at twice 3B, which would be 6B. And what we'll see here is in this simple case here, we can actually get away with sampling at a rate of 2B, and in fact, not only can we get away with that, but it actually does the downshifting for us. Now, this is not a particularly high center frequency, so this thing is just, FL is just twice what the bandwidth is, so it's just barely up. Even if the bandwidth were, say, 50 megahertz, our FL is only at 100 megahertz, and our FH is just at 150. So, although I suppose this could be applied to something like an FM broadcast situation, although in that case B is much smaller. So, anyway, for this simple setup here, just to illustrate how things work, remember, regardless of what that final rule of thumb said, which was that the sampling rate must be twice the highest frequency, what that analysis that we did earlier for standard sampling really showed us was that when we sample, that we should think of the resulting spectrum as the original spectrum plus a bunch of frequency shifted versions. And they're shifted by integer multiples of fs. So that was what we saw was coming out of that impulse generator halfway through the DAC. And so let's take a look. If we have this signal and we actually sample at just fs is equal to 2b, so now we're looking at twice the bandwidth, not twice the highest frequency. For a low-pass signal, that those requirements are one and the same. The bandwidth would be equal to the highest frequency. But in this case, for a bandpass signal, the bandwidth is not equal to the highest frequency. So if we sample at 2b, we're going to get this original spectrum shifted by integer multiples of 2b. So if we imagine shifting this by plus and minus fs, let's see, let's get rid of all this stuff here for a moment. So if we shift by plus and minus fs, that's one of the terms, that's one of the spectral replicas. Since fs is 2b, we would see this move up to here, this move up to here, and then for the shifting by in the other direction, this would move down to here and this would move down to there. That's the scenario that we would end up with for the shift by plus and minus fs. If we do the plus and minus 2fs, we get something that looks like this, and I've kind of color coded and texture coded these things. So both of these get shifted up to this and shifted down to that in that case. And then if we do the shift by plus and minus 3fs, I can't really show, well, I didn't have the space to show the other half of each of these, but this is the lower half, and there would be another one up here. This is the upper half, and there would be another one out here. So I just didn't show those. And then the theory says that we add all of these things up. And so if we add up the original, so that, if you remember, we had a summation k equal minus infinity to infinity of x of f plus kfs. That's the equation that we're talking about here. So we're going to add this, plus all the other ones, but those are the ones that will show us what we end up with. And when we do that, we get a spectrum that looks like this. And if we look very carefully, we look between minus fs to fs over 2. Now remember, this would be the same thing that we would see in a DTFT if we looked at the samples and looked between minus pi to plus pi. We would see this from the DTFT. So what we see is that even though we've sampled this not twice the highest frequency but twice b, we get what's called as a bandpass sampled signal, and it looks like a downshifted version of the RF signal. So we've got the upper band here, and we've got the lower band here, or the negative frequency band here. And then, as is typical, the next step, as we discussed in the last set of notes, the next thing that we would want to do from a processing point of view is get rid of one of these sides or the other. Remember, we're focusing on the minus fs over 2 to the fs over 2 part. So we could get rid of this part and then take this part and shift it down so that we end up getting something that looks like this. Now we're at minus fs over 4 to fs over 4. Something like that. That would be where this frequency is and this frequency is. And we're actually a little oversampled at that point. So we could, as we talked about in one of the earlier sets of notes, reduce the sampling rate by a factor of 2 at this point. So this would give us the equivalent low-pass signal at this point. So bandpass sampling is a preliminary step that replaces a lot of that could be used in principle to replace the electronics, the analog electronics that does the downshifting, the frequency downshifting involved in creating the equivalent low-pass signal. Let's look at a couple specific cases. So that was one very specific case, but now just look at where FH is equal to K times B, where K is an odd integer. And since FL is just 1B below FH, we know that FL will be equal to K minus 1 times B, and K minus 1 in this case would be even. This should be well, I don't know what I'm using F2 to be in this case. Yeah, sorry about that. I think I've combined two of my sets of notes here without. So whenever F2 is equal to LB, we can choose. Yeah, so I'm not sure what I'm referring to as F2 there. I think it's. I think this is supposed to be FH is equal to K times B. I borrowed some notes and thought I had changed them all to the notation used in Proachus and Monolacus. So then we can choose Fs is equal to 2B to perfectly interweave these spectral replicas. And this is the case that we get. And in this case, we have FH is equal to KB and K is odd. Yeah, in fact, I'm absolutely certain that that's what I intended there. So this is exactly the scenario that we just saw on the previous page. So this can be handled very nicely, and although things look like things are set up a little too perfectly here, not only do we have a signal that's a bandwidth of B, but its edges are perfectly aligned with integer multiples of B. So that might be a little bit hard to get exactly, and we'll see how to do that in just a little bit. But let's continue. Yeah, so here this should be K, not L, and this should be K, not L. So let's look at the scenario where FH is equal to K times B, where K is even. And so the picture I'm showing here, K is equal to 6. If we look at the shifted spectral replicas, we'll see that they interweave perfectly. However, if we look at our minus Fs over 2 to Fs over 2, we don't see the same kind of shape. We see that this is actually moved over here, and this is actually moved over here. So in some sense, we get some sort of flipped spectrum. However, this isn't really an issue, as we discussed just a minute ago. What really happens next is that we take this and we can get rid of one side or the other. So we could get rid of this side, keep this side, and shift it up to be centered like this, and we see that we end up with the equivalent low-pass signal structure for the original spectrum. So everything works okay. So we just need to know which way to shift, whether we're shifting down, which we did for when K was even, or I'm sorry, odd, or shifting up when K is even. And that can all be figured out based upon the scenario that you're designing for. So either way, this bandpass sampling looks like it has some potential, even though we've only looked at some very simple, very constrained cases here. And again, the intent is to let the shifting caused by the spectral shifting caused by the sampling to take the place of frequency shifting that we would ordinarily do with oscillators and mixers and so forth. And so the goal is to reduce the actual parts count, especially analog electronics parts count. Okay, so now let's look at the general setting here. Proacus and Monolacus use these capital Fs, and I'm going to continue using lowercase f's, just because I don't like these uppercase F's. So anyway, suppose we start off with a spectrum that looks like this. It has bandwidth B, has some lower frequency FL and some upper frequency FH. And FL and FH are not necessarily lying on the grid of integer multiples of B like we've looked at in the two previous examples. So we'd like to analyze this general setting and see what ends up happening. So we know that we're going to get a spectral replica here and here that come from this being shifted up to here and shifted up to there. So we can pretty easily figure out where that has to end up lying. So if we go from this edge up to this edge where that needs to be shifted to, and likewise, let me see here, if we go from this edge up to this edge where that next one is, we can see, we can puzzle out that one of those is going to be k minus 1 times fs, and the other one is going to be k times fs. So we have those two edges nailed down. Let me get rid of some of this stuff here first. So we've got those two edges nailed down. We know where this edge is going to be, and we know where this edge is going to be. Well, we know what that distance is going to be. Then we know that this distance from here up to here has to be 2FL, and the distance from here up to here has to be 2FH. So using those four distances, all measured relative to this up to various points up here, we can determine that the requirement, let me try to get rid of some of this stuff here, the requirement that we need for this replica and this replica not to overlap this replica is the following. So if we zoom in here, if we zoom in on this area here and this area here, we can see that the red requirements here lead to the fact that KFS, so that's this edge, this distance, must be bigger than where this edge is, which is 2FH. So that gives us that inequality. Looking at the blue ones, we get the second inequality. And then combining those together, we get a constraint on Fs. Now, of course, this still depends upon K, so we don't know what our ability to choose K is, if there's any restrictions. And so obviously, the larger K we're able to use, the smaller Fs is that we're able to use. You can see that just from this constraint right here. So from the point of view of kind of bandpass sampling, our desire is to use as large a K as possible, because that allows us to use a lower sampling rate and achieve this kind of bandpass sampling that we're looking at. All right, going slide, we can continue to analyze this. So here's those two conditions just written separately, and I don't do anything to the blue one other than just write FL as FH minus B. And then this one I'm just going to flip around a little bit. I'm going to flip FS over there and flip 2FH over there to get this condition. So I still have the two conditions that constrain the choice of Fs. And what I'm going to do is basically try to solve these for a constraint on K. So what I'm going to do is multiply A times B. So I'll multiply the left-hand sides, I'll multiply the right-hand sides, and since they're both the same type of inequality, what that will give me is a new inequality that kind of combines the nature of each of those two individual inequalities. So when I multiply the left sides, oh, I did that again. When I multiply the left sides, I get this, and when I multiply the right sides, I do this. I see that I get an Fs that cancels, and I'm left with just k minus 1. On the right-hand side here, I can see that I get a 2FH canceling with 2FH, so my first term will just be k. I get that there. Then I'm going to have a 2b times k over 2FH. So the 2 cancels, and I'm left with kb over FH. So that's the scenario that we have after multiplying and then simplifying. And then we look at this and we say, well, both of these terms have a, there I go again, both of these terms have a k out in front with something subtracted from it. So if I want the thing on the left to be less than the thing on the right, one must be much, well, not much bigger, but one must be bigger than this quantity here. And so that's what we have stated here, that one must be greater than or equal to kbfh. And then if you solve that for k, you just take this and flip it over to the other side and invert it. You get that k must be less than or equal to fh over b. And since k is an integer, we can find that this can be replaced by the floor of that. But this inequality is fine as long as we just keep in mind that k is an integer. So if we look at these two conditions that we just developed, so we have this one, kind of left bound, right bound for Fs, and we look at also a bound on k, we get this kind of description here that shows us what are the allowable Fs operating points as a function of Fh. So both of these two axes are normalized by b, just makes it easier to actually plot them. So we have Fh over b and we have Fs over b. So if we look at this, we can see that we can operate in any of the white areas that are shown on this plot. So if we're operating down here in this region, and it continues up, we're just simply operating, that's regular sampling. All the others are some form of bandpass sampling, and as we go this way, we're going to more and more extreme nature of bandpass sampling. So if we look at this, suppose we have Fs is equal to, or Fh over b is equal to 6. So now, so that's the line where we have to operate, and we can see that there's multiple choices for Fs. Let me try to clear that up a little bit and draw that a little bit better. So suppose we're operating at Fh over b is equal to 6. We must operate somewhere on that line. And in reality, this keeps going up, and you can see that way up that line is where we would be for Fs is equal to 2Fh. That would be the standard sampling theorem that says twice the highest frequency. But you can see that we could operate with k equal to 1, because this just continues up there. We could operate with k equal to 2, up in this region. We could operate with k equal to 3, k equal to 4, all the way down to k equal to 5, and even right at the tip, k equal to 6. So that's the constraint that's being put on by that requirement there. So this figure really tells us an awful lot about how to choose the appropriate FS, or what are possible FS for given for a given condition, FH and B. Those are really the only two things that we need to know. Okay, so looking at this now, one specific example. Suppose this red line tells us where we need to operate. It tells us what our specific FH is. And I'm just pointing out that this is a dangerous place to operate, because if we're off just a tiny little bit, maybe we don't know what our FH is exactly, or maybe our FS is not exactly correct. We could end up deviating from this operating point and end up with actually going into this forbidden region where we would have aliasing. So any of the gray areas are forbidden, not just those below that horizontal dashed line, which is what it might look like. So if we zoom in on that on the slide, we can see, suppose we're operating here. That's our chosen point. What we want to make sure is that there's enough slop in there that that we won't accidentally end up going outside of this nice little white area into the gray region that is not allowed. So we can essentially think about this as using a guard band. So we have our actual spectrum that goes from some specified FL to some specified FH, and then to just kind of add in a little bit of tolerance, we think about putting a guard band in. So we define the FL prime to be FL minus delta B sub L, FH prime, I think that should be FH. FH prime is FH plus delta B, and then we have our new bandwidth B, which is the old bandwidth plus both of those deviations. And so we can do the same kind of thing, except now we're limiting ourselves to based upon F prime, and basically that ensures that we won't get any closer than what we're showing here in this direction and that direction. So you could do it either way. You could say, well, here's my FL and my FH, and you can analyze it and then pick a point so that you have sufficient distance between the edges of that, or to just automatically ensure that you won't actually have something that is too tight of a tolerance. You can just do things in terms of these new FL and FH with built-in guard bands. Either one gets you to exactly the same kind of scenario. So we alluded to the advantages of bandpass sampling and why we might want to do that. And this just shows that instead of doing something like this, where we've got a mixer, we've got an oscillator, we've got a low-pass filter, and then we do baseband sampling using a regular A to D converter, bandpass sampling, at least in theory, allows us to replace all of that by just a bandpass sampling A to D converter. So the goal is to reduce the number of points or the number of parts that we have in our system. And these things become more digital than analog, although an A to D converter does have some analog stuff in it. It's not quite as analog driven as the classical scenario. But that leads us to looking at the specs for A to D converters. So if you go out and you look for an A to D converter, you can't just use any old A to D converter for this bandpass sampling. So there's two things you need to look at least two things. These are the main things. On the spec sheet, you'll see a sampling rate, and that has nothing to do with the frequency range that you're able to process. It just simply has to do with the fastest rate at which the A to D converter's sampling can be run. And what that does is it sets the widest signal bandwidth that the A to D converter can handle. Then, somewhat confusingly, the A to D converter's bandwidth, not to be confused with the signal bandwidth, which is set by the sampling rate, but the A to D converter's bandwidth sets the highest frequency that the A to D converter's internal electronics can actually process. So if you try to apply this to a very high frequency center frequency signal, your A to D converter may not have a bandwidth that will even pass that kind of signal. So this determines the kind of frequency band that you can operate in. For example, HF, UHF, VHF, etc. And so when you're doing undersampling applications, which is what bandpass sampling is, we are undersampling because we're sampling slower than twice the highest frequency. So this little graphic down here kind of gives us an idea of the difference between baseband sampling and bandpass sampling, with narrow band signals and wide band signals. So baseband sampling with narrow band, we've got something that looks like this. For that case, we only need a low A to D converter bandwidth because we don't have signals that are all the way out here, and we need a low sampling rate because the width of the signal that we're processing is fairly small. Now, continuing on, if we look at again for baseband sampling, if we look at a broader signal, we still need a fairly low A to D converter bandwidth because we're not talking about signals that are way up here. But now, because the bandwidth is a little bit wider, we need a higher A to D converter sampling rate. Now, similarly for bandpass sampling, for both of those, we need a high A to D converter bandwidth because the signal's living out at some very high frequency, maybe HF, UHF, VHF, or higher. But the sampling rate is going to depend upon the width of the signal, not where it resides. So hopefully that gives you a clue as to what you need to look at. And just one final slide. This is by no means a up-to-date A to D converter. This is probably from 15 years or so ago, and so I'm sure they have much better ones now. But this just gives you an idea, and you can see right away on the very first page they're advertising those two key characteristics: the sampling rate, which for this A to D converter has a maximum of 40 megasamples per second, and the A to D converter's bandwidth, which is 250 megahertz. So this particular A to D converter, because of the 40 megasamples per second, could process something that is 20 megahertz wide. That's supposed to be a 20, not a 26, and is centered up around, say, 200 megahertz. This is, by no means saying, achieving the goal of moving the A to D converter right to the output of the antenna, but it's moving towards that. And like I said, this is a fairly old A to D converter. It's been a while since I've had to look up any real ones, but there was a time in my career when I was working in the real world, speccing these things as part of my job. And so this is one that I had looked at for one particular job, and I can't even remember what it was. But I would encourage you to go out and prowl around and look to see, who's got what these days and what are the sampling rates and operating bandwidths for these. All right, so that's it for this set of notes, and we'll see you in the next set.